This short video is called "What is the difference between the R0 and K parameters for COVID-19 and why does it matter?" I've called it part 5 because I did 4 previous videos on the maths of COVID testing. And those 4 previous videos were entitled An Introductory Tutorial on Testing for SARS-CoV-2 Virus from an Engineering Perspective, Parts 1 to 4. You don't need to have watched any of these to understand this particular video. So you're at a socially distanced and fashionable dinner party, London, Beijing, Paris, Hanoi or New York, and somebody says, the R0 basic reproduction number is just so yesterday. Simply everybody is now talking about the new K parameter. But can anybody explain it in simple terms? And you say, yes, I can. So how do you do it? So before we start, let's put everything in perspective as of today, the 8th of July, 2020. Let's look at a tale of two cities. So New York City, 8.4 million people, and Hong Kong, similarly large, 7.5 million people. Both islands, both surrounded by water, and both densely populated. New York City had 18,508 deaths, and Hong Kong had 7 deaths. And now a tale of two countries. The USA with 328.2 million people, and Vietnam, 95.5 million people, somewhere between a quarter and a third the size of the US. The US has 133,000 deaths as of the 8th of July 2020, and Vietnam, 0 deaths. Now you could say this is really a tale of leadership, and I could say a lot about the leadership of President Trump. He did call the virus a hoax. He said it was just like a flu. He also said it's going to disappear. One day it's like a miracle, it will disappear. Or, and then I see the disinfectant. Is there a way we can do something like that by injection, inside, or almost a cleaning? But let's forget President Trump and stick to science. So a review of the basic reproduction number. So R0 really tells us about how fast a virus spreads. The equation is R0 equals beta times tau. And R0, as in many others, will be infected on average by one individual with no population immunity, and that will be over the infectious period. Beta is the rate, the number of infections per unit time, and tau is the average infectious period. And if you look at estimates of R0 in Wuhan, where the outbreak started, we find that it was estimated at roughly an average 3.28. But some journals got averages of up to 7 and some 1.5. So quite a wide range. So let's take an example where R0 is equal to 3. So the red circle, who's infectious, infects 3 other people. Those are the orange circles. Every orange circle infects 3 others. That's the green circles. And every green circle infects 3 others to give the blue circles. So in total, the total number of people infected will be that equation on the right-hand side. And if we put in R0 equals 3, and after 4 generations or 3 infectious periods, the total number infected will be 40. That is, add up all the circles on the left-hand side. If we put 10 generations, n equals 10 into that equation, we find it rises to 30,000. And that's this exponential increase that really is so frightening. So I started plotting the number of infections, or cumulative number of COVID cases in the UK, from the first case on the 31st of January up until the 23rd of March when lockdown was announced. And there was an exponential increase, doubling roughly every 3 days in March 2020. Now, R0 only gives us the rate at which infections will grow or decrease, and it does not tell us the number of currently infected, that's the disease prevalence, or does it tell us how infections are spread, for example, are there super spreaders, etc. So how can R0 help us? Well, in many ways. Look at herd immunity. If you have greater than 100 times 1 minus 1 over R0 percentage of the population immune, that is vaccinated, then the disease will just die out. How does that happen? So without going into any maths, just a simple diagram. Imagine on the left-hand side we have one individual in red who is infectious. He or she will infect 5 others, assuming there's no vaccination and everybody is susceptible within inside the population. So every one individual infects 5 others. Now, if we put that R0 of 5 into the equation, we find that we need 80% vaccination at least in order to get this herd immunity. So how does that work? So there's the one red circle on the left, and it's going to infect 5 others. If you take 80% of 5, you get 4 who are vaccinated. So 4 out of 5 cannot be infected, and only 1 can now be infected. That gives you an effective R0 of 1. So if you have greater vaccination than 100 times 1 minus 1 over R0 percentage, your effective R0 will be less than 1, which means that each person will infect less than one other person, which means that the disease will effectively die out. So R0 can help us in other ways. It can help us with patterns of epidemic growth and mitigation methods. So R0 itself will determine how intensive the policy will have to be, and tau and R0 together will determine the time available to implement suitable intensive controls. So if you have a highly infectious short incubation disease, so large R0, small tau, then you really haven't got time to do much. You have to do it in advance, which means you have to have widespread childhood immunization. If you have less infections, longer incubation agents, so if R0 is smaller and tau is bigger, then you have the time to actually take localized control measures like social distancing, like localized lockdowns, etc. Should emphasize there's significant complexity and uncertainty in R0. So a review in 2017, listed below in the references, identified feasible measles range for R0 is going from 3.7 as high as 203. Now another way R0 can help us is with a dynamic SIR model. So the SIR model, I covered this in one of the previous 4 videos, is 3 nonlinear differential equations. S of t in blue represents those susceptible inside the population to the virus, that is not vaccinated, not immune. I of t represents those currently infected with the virus. And R of t represents those who have recovered or are now dead. There are 2 parameters there, beta and gamma. Beta is the infectious rate, gamma equals 1 over tau, which is the removal rate, and tau is the infectious period. And if you remember in previous slides, we said R0 equals beta times tau. So R0 equals beta divided by gamma, and that's, of course, the reproduction number, which is inherent in that model. And so you get, when you solve those equations, this graph on the right-hand side. Susceptible, those who are susceptible to the virus will always reduce, recovered will always increase, and those that are infected will rise to a peak. And the whole idea is to keep that peak small enough so it doesn't overwhelm the medical services within a particular country. Now we can visualize that as water flow. We look at the number of people who are susceptible. Eventually some of those will become infected, so it's water flowing into another bucket becomes red. The infected will eventually flow into another bucket, which is those that are recovered or dead. Now, if we look at the equation for those susceptible, it's equal to minus beta I of t S of t. So those susceptible, as the water flows down, must always reduce on the right-hand side. Those infected may reduce or increase depending on whether the input is greater than the output or vice versa. And those that recover must always increase. Now if you go back to the first equation beside the blue bucket, you can see that ds of t dt equals minus beta I of t S of t. So that's the rate of flow. Now that rate of flow can go to 0 under 2 conditions. Either S of t is 0, that is all the water is flowing out, that is everybody gets infected eventually, or I of t is 0. So if I of t goes to 0, then you stop water flowing out of susceptible even before it's completely empty. And that's what's happened on the right-hand side. You can see that infected goes to 0 before susceptible has gone to 0. So susceptible levels off at a non-zero value and the virus effectively dies out. So let's have a look in more detail at that water analogy. We have ds by dt, that is the rate of flow from the blue water bucket, equals minus beta I of t S of t. So the minus says it's decreasing, and it's dependent on the number infected and the number that are susceptible. So if we look at the number that are susceptible, why should that increase the rate of flow out of the bucket? Well, the reason is that the more susceptible people you have in the population, the more likely it is that someone who's infected is actually going to meet someone whom they can infect. That is, someone who's not immune or someone who's not vaccinated. And from the water analogy, of course, the higher the level of the water in the top bucket, in blue, the greater the flow coming out into the infected bucket below in red. So as we reduce the number susceptible, reduce the water level, it will flow out slower, which is exactly what you'd expect from basic physics. Now if we look at the infected term I of t in that equation, we see that as you increase the number of infected people, you increase the rate at which susceptible people become infected. And again, that's pretty obvious, because if you have more infected people, it's much more likely that some of them are going to find somebody else that they can infect. The water analogy is not so obvious. So what we have to do there is put a feedback path from the red water bucket into the blue water bucket and say that the higher the level of the red water, the more it will open up the output from the susceptible bucket, as I've just drawn for you now. So there, as we reduce the red level, the output gets smaller and the rate reduces until eventually, if there is nobody in the infected or no water in the infected bucket, then you will cut off the flow from the susceptible bucket. And that's what's happened in that particular case that I've drawn on the right hand side. Those infected go to zero, which means the rate of change goes to zero, which means susceptible levels off at a non-zero value. It is, of course, possible that susceptible could go to zero, in which case all the water would go through, but not in this particular case. And what actually happens will be dependent on that important number R0. So this leads us on to the important term, flatten the curve. And what that means is that you take protective measures so that those infected I of t never rise above the healthcare system capacity. And you do that by taking mitigation measures which reduces R0. So you both flatten the curve and you delay the curve. And that's what's happened in that diagram. So now a little bit more detail about how R0 can help us control the epidemic. So this is a useful acronym, DOTS, D-O-T-S, and it was given in the book The Rules of Contagion by Adam Kurchowski. So R0 is equal to duration times opportunities times transmission probability times susceptibility. So duration is the infectious period for COVID-19, and it's, roughly 7 to 10 days with individual variations. There's not an awful lot that you can do with that, but I do believe that sometimes you can reduce the infectious periods by taking certain measures. But by and large, that's sort of a constant. Opportunities is the average number of opportunities an infected person has each day to spread the virus. So you can reduce that by lockdown or by self-isolation or work from home. You can reduce the number of opportunities. Now let's assuming that you do meet another infected person and you're not infected, then we have what's called the transmission probability. And that's the probability that having had an opportunity, it results in transmission. And you reduce that by social distancing, PPE, and hand washing. And finally, there is susceptibility. And susceptibility refers to those not immune and not vaccinated. And you can reduce susceptibility by vaccination, of course, or antiviral drugs, etc. So that gives you 4 ways in which you can control the epidemic. So let's look at some limitations of R0. Take the first one. R0 is not a property of the virus, but it's of social and environmental conditions, and it is difficult to measure accurately and measure in real time. The other thing is you can have a national number that is low, but you can actually have rising localized R0 numbers inside care homes, hospitals, and localized outbreaks. So the average doesn't tell you about what's happening in these particular institutions like hospitals and care homes. And if I look at the estimates by regions, we can see the variations over different regions. So the lowest estimate goes down to 0.3 for Northern Ireland and up to as high as 1.1 for London. And if you take a very local estimate on the Diamond Princess cruise ship in May 2020, that had a R0 number which was as high as 11. Okay, a second limitation of R0 is that it lags real transmission rates by about a week or more. Secondly, it's not much good having something that's out of date in terms of immediate policy planning and also monitoring the consequences of your policy planning. So you really don't want an R0 that's 7 days or more old, inaccurate, and is just a UK average. Okay, third limitation. So we have geographical variations of R0, but we've also got variations with inside a certain geographical region across individuals. And if we take an example of 1,000 student exam marks, you can have the same average for both, but different variance. So just to remind you, this is the mean, mu x, and sigma x squared is the variance. So there's 1,000 students, and they have exam averages of 50% and a variance of 25%. Here's a second group of students, 1,000 students, who've got a mean of 50, the same mean as the one on the left, but a variance of 4%. So variance tells you the spread about the mean. It tells you how many low values you've got and many high values you've got. The mean does not tell you that. So what we need is an individual reproductive number rather than everyone having the same average reproductive number. As a simple example, the person in red has an individual reproductive number of 2, and he or she infects 2 others in orange. The orange individuals infect 4 others in green, and the green individuals, they have different reproduction numbers, 4, 0, 1, 7, 3, 3, 3, 1, etc. And that leads us on to the important K number. So the K number. Now that we've got these individual reproductive numbers, the K number, or what's called the dispersion parameter, it determines the level of variation of the individual reproductive numbers or secondary infections. So if we look on the bottom left-hand corner, we can see that the individual reproductive numbers go from 1 up to 7. And you might say they're clustered around, I don't know, 3 or 2.5 or something. So it's that range of individual reproductive numbers which is measured by the dispersion parameter. And importantly, it provides a more nuanced view of how the disease is spreading rather than simply tracking if it's spreading via R0. So it's telling us how it's spreading by looking at the distribution of the values for those individual colored circles. Okay, let's look at large and small K numbers. Take a large K number. So the diagram on the left might indicate a large K number. What does that mean? Slight problem with nomenclature here because large K means low variance, that is low dispersion, or high homogeneity means homogeneous, that is most of the values are sort of similar, so there's not a great deal of spread of the reproduction numbers. So a bit of a confusion there with the nomenclature. Large K means low dispersion. And so it's saying a distribution of the secondary cases with low dispersion and a value of K much larger than 1, more homogeneous. And that's what's represented in that particular diagram. So if we take a small K number, so small k means high dispersion, high heterogeneity of individual reproduction numbers. So that means heterogeneous means there's quite a bit of variation here. So small k, again, nomenclature slightly confusing, but it means high dispersion, large variance thing. So in that particular case, we can see the numbers go as low as 0, but they go as high as 16. And what that gives you are these sort of super spreaders, the one in red and the one in green, which is 11. So that diagram represents a few super spreaders with a distribution of secondary cases with high dispersion and a value of k that's much bigger than 1, which is more heterogeneous. So for a small k value, as k drops below 1, heterogeneity increases, and as k decreases, it enlarges the proportion of infected individuals that are either super spreaders or dead enders, those that do not transmit the pathogen. So the super spreaders would be the red 16, the one green one that's an 11, and the dead enders would be those that have got 0 in the circle. So if you have a low K value, then a few people are responsible for large amounts of disease transmission because of this low K value. This is over-dispersed. So in this case, it's the red one 16 and the green one 11. The other thing is that if you have K, which is small value, then you can have, in cases of the 1918 influenza, 40% of infected people will not pass on the virus. So those are the ones that have a 0 inside the circle. They're not actually passing them on. They're called dead enders. And if you look at SARS, MERS, and COVID-19, so you can have K values that might go as lower than 0.1, then the proportion who don't actually pass on the virus, that is the circles with 0, that could rise to 70% or higher, not actually passing on the virus. So a low K value that's over-dispersed increases heterogeneity and increases the probability of outbreak extinction. Now, how does that happen? Because as you become less homogeneous, you get these few super spreaders, you get the dead enders, and eventually, as you get more dead enders, then you increase the chance that the virus might actually extinguish itself. And we'll see that later when we look at the maths in more detail. So knowing K is very important because it informs public health measures. So the K value helps to inform what sort of public health measures may help to reduce R0. So if we can identify and reduce the situations that are disproportionately driving transmission, then that actually suggests we could have potentially quite a lot less disruptive measures in place, but still keep the reproduction number low. So that means that K allows us to take localized activity rather than, say, complete national lockdown or stay at home. So we now need to look at the maths behind the K dispersion parameter. So far, it's all been descriptive and not mathematical. Some of you may turn off, but actually this is the most interesting part. In order to see where K comes from and how we estimate it, etc., we need to look at both discrete and continuous distributions like Poisson, gamma, and the negative binomial. So I'm just going to introduce enough maths in order to understand the analytical stuff that comes next. So let us examine what K tells us then about various diseases and how a small minority of people can be super spreaders, the probability of epidemic extinction, etc. So we need to look at 3 random variables and their distributions. We need these for further derivations, so I'm keeping the maths to a minimum. So the first random variable is the Poisson random variable, or Poisson distribution. And we write it as above, x tilde Poisson brackets lambda. Lambda is called the intensity. And this is a discrete random variable. Discrete because it either has a finite number of values or a countable infinite number of values. So it's like tossing a die which has 6 possible outcomes. So that's the equation. It's a probability mass function, probability that x is equal to k, and the intensity lambda is normally greater than 0, and the mean value and the variance are both the same. They're equal to lambda, the intensity parameter. And if you were to plot that probability mass function, you can see that as you increase lambda, you increase both the mean and you increase the variance. So they're not independent and cannot be controlled separately. So the next distribution is called the gamma distribution, and it's a continuous distribution. That means that the random variable x, you cannot say probably that x equals 4 or 4.6. It's a density function, and so you have to take the PDF and integrate, say, between a and b to give the probability that x is greater than or equal to a, less than or equal to b. And we write that distribution as x tilde gamma brackets k, comma, theta close brackets. So there's an expression for the probability density function. And at the bottom you have, in the denominator, you have capital gamma k. If we write down capital gamma z, it's an integral to evaluate that unless z is integer, in which case it's a factorial. K is the shape parameter and theta is called the scale parameter. And the mean is k theta and the variance is k theta squared. And here's an example of the PDF as we change the values of k and theta. And finally, we introduce what's called the dispersion parameter. So this is the k number I was talking about. In this particular case, for our gamma function, I've called it k subscript 1 to distinguish it from the dispersion parameter for the next distribution, which is the negative binomial. Now, the strange thing is that it's related to the variance because sigma x squared equals mu of x squared over k1. So if you keep the mean constant, then the dispersion parameter is inversely proportional to the variance. So I've done just that here. I've kept the mean constant at 1.5 and I've looked at the gamma distribution parameterized on the dispersion coefficient k1. So as k1 gets bigger and bigger, then the variance gets smaller and smaller. I should point out that this definition of k1 on the previous slide, which is equal to small k, is different than in some other papers. So there seems to be a bit of confusion. I'm using the definition that's used on the reference below at the bottom of this page. So finally, the final distribution is the negative binomial distribution. And there are different definitions for this again. It's always a bit confusing with these distributions. This is discrete, and we write it as x tilde nb, negative binomial, brackets r comma p, close brackets. So r and p are the two parameters that you have to enter to plot the negative binomial distribution. So it's written like that. And the mean is given there, equal PR over 1 minus P, and the variance equals PR over 1 minus P squared. And the limiting case is well known. As you let R go to infinity, you end up going from a negative binomial to a Poisson. We're not going to use that. I just put that in out of interest. The dispersion parameter, here we say K2, and again I'm using K subscript 2 to differentiate it from the dispersion parameter for the gamma distribution, is equal to R. Again, some papers use a different definition, but this is the one I'm using here. And so we get sigma x squared equals mu x into 1 plus mu x over k2. So like the previous gamma distribution, we find that the variance, as you increase k2, the variance reduces. So as you increase the dispersion parameter, the variance goes down. And here's a simulation, keeping mu x equal to 10, and we're changing r, and the variance is reducing. Now, I find this somewhere on the web, and I can't remember where, so I would really like to credit the author, but I can't find out who he or she is to credit them. Sorry about that. So having defined those three distributions, remind ourselves what we're trying to do here. We're trying to go from having a common reproductive number to looking at individual reproductive numbers, because the common average reproductive number can obscure considerable individual variation in infectiousness. So the individual reproductive number V, which we introduced before, I didn't say it, but it's actually a random variable. So there's the traditional approach, where R0 is the average number of infections that any individual will make over the infectious period. So R0 secondary infections on average. It doesn't mean you always infect. If R0 is equal to 3, you always infect 3. You might infect 3.5, 4.6, but the average will be 3. So now what we move to is we say that each person will have an individual reproductive number V, and they will produce Z secondary infections. However, here's the difference, that V is now a random variable. What type of random variable is it? Well, we're going to see there are different candidates for the probability density function of this random variable. And how do we go from V to the number of secondary infections? Well, we say that Z is a Poisson random variable, and its intensity is V. So if I was to take a V from this distribution, which was say 7, I would put 7 in there and get Z. Then if I did another realization of V, I might get 2.4. I put 2.4 in again, and I get another Z. The important thing is that V is not fixed. V is a random variable. So that's a summary of what I've just said. So now, what are the different PDFs for V? And again, refer to the references down below. So Z secondary infections, and we're saying that Z is a Poisson distributed random variable based on V, which himself is a random variable, and the expected value of V is R0. That's important. So we say the expected value of V is equal to some value which we're going to call R0. So three possibilities which are mentioned in the papers below. So we could take V equals R0, a constant. So if we take it as a constant, then we've got the traditional way of looking at the reproductive number. In this case, Z is equal to Poisson R0. So Z itself is a random variable, but the expected value is R0. And that's the traditional way of doing it. We say R0 is the average number that you infect. Another way of looking at it is consider V to be exponentially distributed. Now, I didn't cover exponential random variables because I'm not going to be dealing with that. Neither did I cover geometric random variables, which is what will happen if you put Z as a Poisson random variable based on an intensity of V. The most general approach is V is gamma distributed. So if V is a gamma distributed random variable, it turns out that Z equals Poisson V, is a negative binomial random variable with expected value of Z equals R0. So important thing there, the expected value of the individual reproductive number V is equal to R0, and also the expected value of Z, the secondary infections, is equal to R0. So let's look at that particular case of V being gamma distributed. So there's V, and we're assuming that it's gamma distributed. So we're parameterizing that on the dispersion parameter K1. You've seen that plot before. And as we increase K1, then what happens is that the sort of variance of the distribution gets smaller and smaller. It becomes more homogeneous. Then we take Z, which is the Poisson distribution with an intensity of V. And if we do that, we find that the resulting Z, that is the number of secondary infections, is itself a negative binomial. So that's not obvious. It's not obvious where you have a parameter of the Poisson distribution, the intensity, which itself is a random variable. How do you find the resulting distribution? So let's have a quick look at that. So we write down that Z equals Poisson V, where V is gamma distributed, with a mean of R0. And so what we end up with is really the equation on the second line, the probability that Z equals K, that integral, and P2 of V is simply the gamma distribution. So if you do that integration, you end up getting a negative binomial. Now, I haven't done it for you because I've assumed that it's correct, which I think it is, but you can model it using MATLAB just to verify for yourself, if not prove, that this is what actually happens. So we can also, just to note, we can also parameterize the gamma distribution in terms of its mean value, R0, and the dispersion parameter. So that's often used as well. So I've included that. So let's put the gamma dispersion parameter K1 to work now. We've defined what this dispersion parameter is for the gamma distribution. We've explained what the individual reproductive number is. It's a random variable. How can we actually use it to our advantage? So if we have a large K1, to remind yourself that's underdispersed, it means that you have a range of values for the red and the blue and the orange, the green, which there's not a great lot of difference between them. If you have a small K1, it's overdispersed, you get a large range of differences, and you get super spreaders. That can lead to a few people creating a lot of transmission, and it can also, because of the zeros, lead to extinction of the virus. So we're going to look at two examples of how we can use the K dispersion parameter. We're going to see that small parameters mean some super spreaders. So nearly 90% of SARS infections came from 20% of infected cases, and that's due to the small dispersion parameter for SARS. That means that if you could identify those 20% and isolate them, you could get rid of 90% of infections. That was roughly 2003 when the SARS epidemic occurred. So let's have a look at this plot. We're looking at different diseases: SARS, measles, smallpox, monkeypox, pneumonic plague, and what I call a homogeneous population. Along the bottom axis, the x-axis, we're looking at the proportion of infected cases ranked. So 0.2 means 20% of most infectious, 0.4 means 40% of the most infectious cases. And you're looking at what sort of expected proportion of transmission you will get from those 20%. So in a homogeneous population, what you could expect is that the 20% of infectious cases would give you 20% of transmission. However, as you start reducing the K number, then what happens is that you tend to get disproportionately more transmission from a small number of very infectious cases. So these graphs are parameterized on K1, so decreasing K1. So the highest K1 is for the homogeneous population, and the lowest K1 here is for the SARS epidemic. And the homogeneous population, again, it's Z, the number of secondary infections, is equal to a Poisson distribution with intensity V. In this case, we let V, instead of letting it be a random number, we just let it equal to R0. So that's the traditional average reproductive number across all of the population. So if we take 20% of the most infectious cases, then for SARS, that's giving us just under 90% of transmission. So if we increase the K1 for monkeypox, we find that 20% there of the most infectious cases gives you slightly greater than 60% of transmission. And of course, if you have a homogeneous population, then 20% of the most infectious cases gives you 20% of the expected proportion of transmission. Now, what we've done on the right-hand side is we've plotted dispersion parameter K1 along the x-axis. That's a logarithmic plot, by the way. And on the y-axis, we've the proportion of transmissions due to the most infectious 20% of cases. So we've taken the most 20% of cases, the most infectious 20% of cases. So here we have it. If we look at SARS, we can see that 90%, as you already know, we can see that 90% of transmission is due to 20% of the cases, and that's with a K number of somewhere between 0.01 and 0.02. And if we go down to pneumonic plague, we can see that, as we already know, the proportion of transmission due to the most infectious 20% of cases, we're talking there about 50, that's about 0.5, 50%, and the dispersion parameter is just bigger than 0.1. So heterogeneity across individual reproduction numbers increases as K1 reduces due to a higher proportion of non-transmitting cases when V is over-dispersed. So the second example of how we can use the K number, or the dispersion parameter, is looking at outbreak extinction. This is the notion that eventually the virus will become extinct, and how that can be, the probability of that happening can be affected by the K number, or the dispersion parameter. So in figure A, what I've done is I've just plotted the PDF for V, where V is the individual reproductive number, parameterized on K1, which is the gamma dispersion parameter, and R0, which is the expected value of the individual reproductive number. We've seen this before. And as K1 increases, we get less variance in V. Now, if we look on the right-hand side, what I'm now looking at there is the basic reproductive number on the x-axis and the probability of extinction, Q, on the y-axis. And we've parameterized that on K1, the dispersion parameter for that gamma distribution on the left-hand side. Now, we notice that all the curves meet for R0 equals 1, because once you have a basic reproduction number of R0 less than 1, then the probability of extinction is 1, because we know from earlier slides that if R0 is less than 1, means each individual is infecting less than one person, and eventually you will get extinction. But how do you get extinction, or how do you increase the probability of extinction when R0 is bigger than 1? So let's have a look. Let's take the case where K1 is equal to 1. So we've got a dispersion parameter of K1 equals 1. Let's see what happens as we increase R0. So as we increase R0, we can see that the probability of extinction decreases. So that means it's more likely not to go extinct. And the reason for that is because irrespective of the K1 value, as you increase the basic reproductive number, it means on average, you're infecting more and more people. So as you infect more and more people, it's much more likely that you're not going to get extinction of the virus. Now, if I set the reproductive number to 3, so let's assume I have a fixed reproductive number, and I start changing the value for K1, what happens then? So what I'm doing here is I'm reducing the value for K1. And as I reduce the value for K1, what happens? We can see that the probability of extinction increases. So why is that? Well, to understand that, you need to look at figure A. So as we make K1 smaller and smaller and smaller, what we're doing is we're getting an over-dispersed system. So we're having this idea of super spreaders, but also dead enders. So that's ones with 0. So it means that as you reduce K1, you get greater dispersion, but you also get a chance that you're going to hit a lot of these individual reproductive numbers of 0, and so increase the probability of extinction. Now it looks like the very last red line with that red dot on it has a probability of extinction of 1, but it's not actually 1 for K1 equals 0.01 and R0 equals 3. It's actually slightly less than 1 if you were to look at that very, very accurately. So in summary, probability of stochastic extinction, that's the probability that an infectious disease will disappear from a population at the end of a major outbreak, that's called fade out, versus reproductive number R0. As R0 increases, the probability of extinction decreases. As the gamma distribution dispersion parameter K1 reduces, the probability of extinction increases due to a higher proportion of non-transmitting cases when individual reproduction number V is over-dispersed. That means when K sub 1 is small. So we've explained how we can use R0 and K1 in terms of analysing pandemic spread or mitigating the pandemic effects. But why do we need to estimate R0 and K1, and how do we estimate it? Because we have to know what these values are in real time. So real-time tracking of these parameters by statistical modelers is essential to predict the virus, both predict the virus and help with mitigation measures. And this means that we need accurate data of COVID-19 infections, and we get that via test and track, which has been very controversial in the UK. And if we don't have that, the models won't provide accurate estimates of R0 and K1. And this modelling information feeds directly to the UK SAGE subgroup, Scientific Pandemic Influenza subgroup on modelling, SPIM, and to the Regional Public Health England teams. So how do we estimate R0 and K1? We said why we need to estimate. How do we do it? So in terms of just general theory of estimation of any unknown parameter, we can use many of the mathematical techniques that already exist, maximum likelihood, sequential Bayesian techniques, etc. But just for a very simple illustration in a sort of non-mathematical way, let's consider tuning the parameters of the SIR model we've already talked about to fit the reported data and thus estimate R0, because we know that R0 is included in the 2 parameters of the SIR model. So there's the SIR model again, and there's the 2 important parameters beta and gamma, and we know that R sub 0 is equal to beta over gamma. So if we take the data for S in blue, the data for I in red, and the data for R in green, and we try to fit the model to that, and we do that by adjusting beta and gamma in an approximate way because it'll never fit exactly, then we could have some estimate of beta and gamma and thus R0. So the little hat above R0 means the estimate of R0 is equal to beta hat over gamma hat. Those are two estimates, and that's the reproduction number estimate. And this was done in the reference below for the first week of the pandemic in Iran, February 2020. And in that particular case, the estimate of R0 was 4.86. And that's very high. That explains why Iran had such a difficult time at the very beginning. So let's have a summary of what we've learnt. So we started with the idea of a common R0 number across the whole of the population. And then we said that really this average isn't much good. What we need is an individual reproductive number, which is a random variable v, whose expected value is R0. And the K1 will tell us how much those individual numbers spread. So what we need is accurate estimation of the parameters like R0, which will tell us if the virus is spreading or not, depending whether it's greater than 1 or less than 1. But more importantly, K1, which will give us more nuanced information about how the virus is spreading. And this is essential to understanding and controlling the pandemic and taking those mitigation measures that are so important. And all of this, of course, cannot be done without fast and accurate localized test and trace data across the UK and in other countries in the world as well. So scientists advise, but politicians must deliver. And you could ask yourself the question, have we got the world political leadership that we deserve? So, back to that dinner party where it all started. And that concludes my explanation of the K dispersion parameter. And everybody at the fashionable dinner party is just so impressed with your explanation. Okay, that's the end. Thank you so much for listening. Keep safe and sorry for any mistakes.